Hi guys, I thought it wouldn't be a bad idea to do a new weekend project, or I should say to make a new weekend project, since I'm waiting for all sorts of parts, replacement parts, to continue work on the RCA TV. So yeah, well, I thought we would all enjoy, you and me together, to make something else. I thought long and hard about what sort of weekend project I would make, and then I suddenly had a sort of a flash, an insight, which is this: that if you take a good look on the internet, and specifically on sites like eBay and all that, you'll see that the magic eye tubes for vintage radios have gone through the roof. I mean, if you take a eye tube, a very well-known type of eye tube, which is the EM34, you'll see prices range from between $30 for an old used one to over $100 for a new old stock one. And unless the radio is really a rare and exceptional model, I don't think most of us would be willing to spend $100 on one single tube, unless, you know, like I said, the radio is so rare and so exceptional that doing or making the expense of $100 for a single tube is a valid one. Now, most radios are nice, but in my opinion do not deserve to be upgraded with a tube of $100. Okay, so that's ridiculous. So I thought, okay, what would be the next best thing? Well, I thought, why not give the radios a period correct update? And I mean by that, using visible parts that were available in the late 50s or the early 60s, that would allow us to update the radios and without destroying them, or without really altering their basic functioning. And so I came up with this idea: why don't we make an alternative kind of magic eye tube for our tube radios using this? Yes, I think you all guessed what this is. This is a tiny Nixie tube, and in fact it's one of the smaller models. Okay, this is an IN2 model, which has basically all the numbers from 1 to 9, or I should say from 0 to 9, and it even has, if I'm not mistaken, a decimal point, and that's about it. Okay, but we don't need much more than this, and I'll show you why, or rather I'll explain to you why. Okay, well, like I said, what we want is to make something which would replace the magic eye tube in a radio. Okay, and if we look at how a magic eye functions, really, I mean visibly functions, it's nothing more than a round gauge with a central dark spot, and then all sorts of, well, a kind of a green area, or you could say a green neon light area, which opens up like this. Well, I don't have to explain too much to you guys what a magic eye looks like. I'm sure you all know that it does something like this. Okay, so this is more or less what it does. Yeah, and as the signal gets stronger, the gap between the left and the right's green neon light gets smaller or gets larger, right? Right. Now, I'm not going to go into the working of a magic eye tube, only for in as much as it is important to our weekend project, but not more than that. If you want to read on the working of a magic eye tube, there are plenty of very well documented sites out there on the internet. Anyway, draw it like this. You have a grid which is positioned between an anode on this side, okay, and you have a couple of smaller anodes which are often pictured like this. Okay, now you also have a cathode, which is here, and what happens is that the big anode is at B+, and the smaller anodes are also at B+, and you have a couple of anodes for the left side of the tube, and you have a couple of anodes for the right side of the tube, and both of these are also connected up to B+. So what happens is that electrons shoot off from the cathode in the direction of the anodes, accelerated by the big anode on the other side of the tube. Okay, and they are deflected to the smaller anodes, which you see here, in such a way that you have roughly half of the electrons hitting the left part of the screen, so two little anodes. So you could see the screen of a magic eye as being two halves like this. Okay, something like this. And the electrons shoot off either in this direction, yeah, or in this direction. And according to the potential, which is on the grid, which is mostly a negative potential, yeah, you could say V minus, okay, you can modulate the amount of electrons that hit both halves of the magic eye tube. So that's why you can have a signal as small as this, both sides, and it's always symmetrical in these round eyes. Or you can have something like this, okay, which is more common. Okay, so you would have something like this. So what's important to us is not so much what happens with the anode voltage, and in particular of the two smaller anodes. What is more important to us is the B+ on the big anode, yeah, which accelerates the electrons and which we will repurpose for our design, and the filament voltage, which is 6.3 volts most of the time, AC, which we will repurpose for our design. Okay? So, what is of interest to us to design our Nixie tube magic eye is the B+ voltage of the big anode, the V- that goes to the grid, and the filament voltage which goes to the filaments, which is 6.3 volts AC. Now this V- voltage can be anything between, say, 0 volts and minus 40 volts or something like that. So, which is at this point not yet critical, but it's good to remember. So let's say so from 0 to minus 40 volts. Okay. The B+, well, that can vary from radio to radio, but I would say that the B+ is somewhere in the region of the 250 volts plus. Okay, and the AC voltage 6.3 volts. Right. So that's basically how a magic eye tube works, with electrons being accelerated to little anodes on each side of the tube surface, yeah, and being accelerated even more by a big anode at the end. Okay, so you could say the little anodes really deflect the electrons, whereas the grid modulates how many electrons will effectively hit the screen. Yeah, so the more negative the grid is, the less electrons will fly off and be deflected by the little anodes you see here. Okay, right, so that's basically what we need to remember of the magic eye's functioning. Now, in order to have something which would serve more or less in the same way a magic eye tube does, which is that the magic eye tube, you have in a magic eye tube you have an opening of green luminescent gas that opens up or closes more in function of the signal strength, which in turn modulates the grid voltage inside the magic eye tube. Okay, what we want to do is to measure that varying voltage and translate it into something which we can send to a Nixie tube digit. Okay, so depending on the strength of the signal, we want the digits of the Nixie to go from, say, 1 to 9 or 0 to 9. Right? Okay. So we need to translate that varying signal, which comes to actually to the grid of the magic eye tube, into something we can use to drive our Nixie tube. And there is in fact something like that on the market, and that something is this: an LM3915 integrated circuit. Now this is it in real, so it's an 18-pin chip. Okay, And what it really does, without going too much into detail on what's inside of this, you can find a data sheet for it on the internet. Just type in LM3915 and you'll get a whole slew of data sheets for nothing. Okay, so basically what the chip does is this. It takes in a signal at pin 5, you see here, and it compares internally the strength of the input signal, so in fact a voltage. It compares that voltage to a reference voltage, okay? A reference voltage which it generates itself. Now, I'm not entirely certain. I need to read up a little bit more on the LM, but I think you can set the reference voltage between anything from 0.1 volts to 1.2 volts. Yeah. Now, the reason why that is important is that you need to set the voltage steps you want to measure. Okay, so if in the hypothetical situation that a voltage that we need to measure can vary from 0 radio signal strength to maximum, that would translate from 0 volts to minus 40 volts. If we want to be able to measure this voltage in steps of, say, 4 volts, then we need to set the internal comparator, which is inside, which is really a series of op-amps, yeah, in such a way that they switch on one after the other. For every 4 volts the signal increases. And if we set it in such a way that the outputs switch on with increasing voltage, then what we get is that each output of the LM3915, yeah, goes low, so in fact sinks current into it. Okay, and there's even a mode pin, which you see here, which allows you to choose between bar and dot mode, which means that you can keep each output active and every next one as well. So if you would, like this schematic, put an LED on each output and you put it in bar mode, then with mounting voltage each LED would from 1 to 10 would switch on and stay on. So if you measure, say, 1 volt and 1 LED, 2 volts, 2 LEDs on, 3 volt, 3 LEDs on, etc. Obviously, the bar mode is not something useful to us. We don't want to display a bar. We want to display digits, one after the other. And happily for us, there's also something which is called a dot mode, which means that with mounting voltage, only one output in turn is pulled low, yeah, is pulled to ground or sinks current, which is ideal for us because that means we can switch on digits one after the other, so from 0 to 9, 0, 1, 2, 3, etc. Which would allow us to display on this little tube digits in mounting order as the signal strength increases. So in effect you would see a number appear, say 1, and then as you tune in to a radio station you would quickly see the number mount from 1 to say 7, with all the steps in between. So 1, 2, 3, 4, 5, 6, 7. Yeah, depending on how quickly the signal, of course, mounts. If it goes really quickly, you'll never see the transition between 1 and 7. You'll just see the 1 change into a 7, of course. Okay, so what I need to do now first on our breadboard here is to make a basic circuit that works more or less like this. Now, mind you, this circuit here, I didn't invent it, okay? This is not my invention, or this is not my design. This is simply something I took out of the data sheet of this chip. Okay, so what I'm going to try now first is to set it up to work normally for with an LED and with high voltage. Okay, and once I make it work normally with high voltage and LEDs, then we'll transform the circuitry in such a way that it can drive this tiny little Nixie tube. So that will be the next step. Alright, I hooked up the LM3915 the way it's described in the data sheet, okay, like this. Don't worry, I'll show the schematic later on. And I also hooked up the little transistor which is connected to the V+, which is, you could say, something like a voltage regulator circuit, okay, with a small LED which shows you roughly whether there's a lot of current and voltage running through it to the chip or not. Right, that's actually not so relevant to this demo, but we'll see later on. Anyway, what else did I do? I hooked up 5 LEDs to the outputs of the chip. Now, I didn't hook up the full 10 LEDs, well, because there's not enough space on this breadboard, and also you know, I'm showing the voltages and all the even voltage steps, which is more than enough to demonstrate how the thing works, okay? And then finally I hooked up my other variable power supply. So this small one here supplies the circuitry with working voltage. This is connected to my big power supply, which I can vary in output voltage between 0 and 30 volts if I wanted to. Now, remember, the chip is designed to measure any kind of voltage between 0 and 1.2 volts, basically. So, if you want to measure any higher voltages, you need to build a small voltage divider with resistors to be able to do that. But no problem for the moment. What suffice to know that we're going to demonstrate how the chip senses voltage increases, even if they are really tiny increases. Okay, so I'm going to switch off the light for a moment. Okay, so this here is that which you see in the upper right corner is the small power supply. Okay, so watch the tiny little light you see somewhere in the center of the screen. Okay, so I'm going to turn up the voltage now. There you go. The first LED switch is on. Okay, now the second one. Now the third one. Now the fourth one. And we're at about 0.7 volts now. And now the last one. And I'm at 1.2 volts. Okay, so if I would turn up the power supply even more, say to 2 volts, well, like this, nothing really changes. So that's what I said. The chip is designed basically to show any variation of voltage between 0 and 1.2 volts. So you could say it ignores any voltages either above 1.2 or below 0. Okay, here I go back down again. Alright, this is 1.2. This is 0.8. 0.3 or thereabouts. 0.1. This is probably half a volt, but I can't see it on my power supply. And this is 0. Right. So you see that it works perfectly, okay? So, and it has a rather fast response speed. So as I vary the power myself manually from low to high, you can see the LEDs following the signal quickly. Okay, so it has a very fast response time, faster than we will ever need for our little design here. Okay, well, this is nice. So what's the next step? Well, the next step is to see whether we can hook up the Nixie tube to this circuit and have it function with the circuitry you see here instead of with the LEDs. I made an executive decision that I would not use in any sort of way the filament power to power my design for a number of reasons. The first reason is that filament power in a radio or in a TV most of the time is 6.3 volts AC, and since this circuit here is meant to measure something which is in the B plus circuitry, I don't want to introduce, even inadvertently, hum or other sort of noise in the B plus. So I'm not going to use the filament power unless I find a way of filtering it in such a way that it doesn't take too much space and therefore can still be used. But I think in any case it wouldn't be such a good idea to mix filament voltage with B plus voltage. Okay, the next reason is, of course, that if I use only one power line, so to speak, to power the whole design, then it will simplify the circuitry quite a bit. And oh, by the way, don't mind this part right here, okay? I'm just using it to recreate a kind of B plus. As you can see, I'm rectifying the power which comes from my variac, and right now I'm generating about 241 volts B plus. Okay, well, simulated B plus. Okay, the next thing that I wanted to do, obviously, aside from powering it up with B plus, is to keep the amount of current the design would draw to a minimum. Now, obviously, with the LEDs in the circuitry, the design uses, I would say, anything between 10 and 20 milliamps, which, in my opinion, is a bit too much. Yeah, I would like to keep it below 10, and if at all, somewhere in the region of 2 to 4 milliamps maximum. So, obviously, the LEDs ultimately will disappear from the design. Okay, they are just there for testing purposes, nothing else. The Nixie tube itself, when it glows, it has a current draw of about 2 milliamps for one digit, which is perfect. I don't want to light up all the digits or 2 or 3 digits, just one will do. And one digit consumes about 2 milliamps of current. Of course, at a rather high voltage, the Nixie glows at around about 130 volts DC. Okay, well, in any case, I had to do a little bit of research as to how to switch the Nixie on and off. And I think I'm pretty close to finding the right let's say mix of parts. Yeah, I'm really close. I did a little bit of calculating, but as you all know, in practice it's quite a different thing quite often from the theory. Anyway, as the proof of concept which you see in front of you proves, the principle does work, and I want to show you. Oh yeah, by the way, I read the whole data sheet I had for the LM3915, and there are two remarks which are important. The first remark I found in the data sheet is that they advise to keep the wiring, if you use any sort of wiring, especially the wiring that goes to the LEDs, or in our case to the Nixie tube over there, as short as possible. And they stress the fact that if the wires are a bit too long, they might pick up hum, yeah, or stray noise, electrical noise, which would make the circuitry, or the chip in this case, quite unstable. The second thing they advise is to put a little electrolytic, and by little I mean somewhere around 2 microfarad over the power that powers the LEDs, so the between ground and plus, which powers the LEDs, to sort of stabilize the circuitry. I might do that, I don't know yet. Until now it works perfectly without a so-called stabilizing capacitor, but well, I'll see. maybe practice will show that I will need it in any case. Okay, now the chip by itself consumes very little power. It is actually designed to consume very little power. And in fact, it already starts to work, say, around 3 volts and a half. Okay. And if I read the datasheet correctly, it consumes a few milliamp. And when I say a few milliamp, or let's say anything between 2 to 6 milliamps, which is really very little. So that, in a sense, sort of puts me at ease with building it and using it ultimately in an old radio, since the B plus transformer in a radio is often built to produce, say, 250 to 300 volts, but never more than, let's say, maximum 50 milliamps or something like that, unless we're talking about a very heavy amplifier or something like that. And in that case, the B plus will be able to draw or to source quite a bit more current. Now, in any case, I think it's good practice to keep the amount of current drawn to a minimum. Okay, the less current you draw, and the less voltage, of course, the less heat you generate. Now, when I talk about heat, I also talk about this power resistor, and it gets quite toasty, believe me. You can't really take it in your fingers. It's really hot. I suspect it's somewhere around 80 to 90 degrees Celsius. So it's quite hot, yeah? Not at water boiling temperature, but really hot. You will burn yourself on this resistor. Now, why do I use this resistor? Well, first of all, I use it to drop the voltage which I get from my simulated B plus circuitry. Okay, so I need to drop voltage from, say, around 240 volts or a little bit more than that to about 4 volts. Okay, so I need to drop 236 volts, and it has to be able to draw say about 10 milliamps, 10, 11, maybe even 12 milliamps, which I calculated that, and that gave me about a power dissipation of 3.7 watt. Now that resistor, that enameled resistor you see here, is 5 watt, an old style wire wound power resistor, and it's 5 watt, and it gets really toasty. I did use a modern 3 watt resistor like this, but this one got so hot, it didn't burn, and as you can see, it didn't char or anything, but it got so hot that it started to smell funny. So I think I was pushing this resistor right up to its limit. Okay, so that's why I'm using an enameled power resistor. No smell, just heat. Now, obviously, the resistor heats up quite a bit because the diodes, the LEDs, I mean, you see in the circuitry, draw quite a bit of current. And that, in combination with the voltage drop I need, produces quite a bit of heat in the drop resistor. So yeah, now once I take the LEDs out of the circuitry, and in any case I won't need any LEDs anymore once the circuitry is finished, the current will drop to about 2 to 3 milliamps, or at least that's what I hope. And power will, power I should say, will drop to a level of about a half watt. And a half watt, no problem. I mean, a resistor like this can easily take 3 watts. So in my opinion it won't even get warm. Right, so that's where I am at. Now the circuitry you see here is the circuitry, the basic circuitry I took from the data sheet. Okay, so it's basically it's this. Okay, I didn't use all the LEDs you see on top of the schematic, but aside from that I did use all the other parts, and it works, and I'll show you that it works. Okay, so watch the row of LEDs. See? As I turn the voltage up, each LED lights up in turn. Okay, let me switch out the lights and you'll see better. Okay, that's one LED. That's the next LED. That's the last LED. Okay, so as you can tell, the circuitry works quite well. Now the goal, of course, is to make the Nixie tube glow. Okay. Now there's very little light right now, and the Nixie tube glows a tiny little bit in the dark. Okay. And I will find a way to eliminate that sort of afterglow as well. Don't worry. But I want to show you now how the circuitry works with the Nixie tube. Okay, so on your left, on the left of the screen, you see the board with the LEDs. Okay, so now I'm going to modulate the voltage which I put into the signal input of the chip. Okay, here we go. That's the first LED. That's the second LED. That's the third LED. And now watch the Nixie. And that's the Nixie. Okay, so I switched the Nixie to the number 4 just to as a test. Okay, so nothing more. But now when I vary the power to the measurement board, I can switch the Nixie on and off. Now the flashes you see in the Nixie are the last problem I have to contend with. Okay, so I have to find a way to sort of prevent the Nixie from glowing while the measured voltage varies. Okay, so that's the last problem really that I will have to fix in my design. Once I manage to fix that, then I'm going to unmount all the parts on the breadboard and put them together on the print board, and then you'll see it function all on its own. And obviously I will give the print board such a shape that it will fit a cylinder which is not larger than, say, a standard EM34 Magic Eye tube, obviously. Anyway, this is where I'm at, and as you can see, I'm pretty close to finding the final design, a good working design. So I guess you'll just have to have a little patience for the next update, so that I can show you the finished design. One thing, guys, and I think, well, I shouldn't have to tell you this, but I will tell it anyway. If you intend to build the Nixie Magic Eye project, which I'm showing you, you do so at your own risk, okay? You're dealing with high voltage. And as you all know, high voltage is deadly. It can and it will kill you if you're careless. Alright? So if you intend to build this, be warned. You're toying with very high and deadly voltage. Right, well, that's it.